steering angle in that state is say theta, and now you choose to steer up at a particular angle theta dash, and you choose to accelerate the vehicle. Whatever action you take is, and that is whatever action you take doesn't matter. You are taking certain actions in this state. Now the effect of these actions will be dependent only on the present situation of the vehicle, that is present speed of the vehicle and the present steering angle of the vehicle, and not on the prior history, that what is the speed of vehicle in state A and state B and what is the steering angle time. It doesn't matter. So what matters is the present state, the present velocity and present steering angle, and the results of the action that you will make in this state will result in a next state. Okay, so this means that this driving process can be represented as MDP. There is Markov decision process. That is, what matters is the present state and not the prior history while making a decision, and the effects are dependent only on the present state. So now comes a value function which we denote by the symbol pi. It is a mapping from states to action. Basically, the pi gives the probability of taking a particular action in a given state S. So this policy represents the probability of taking a particular action A in a given state S. Now suppose if you want to measure that how good it is to follow a policy from a given state S, or suppose if you want to measure that how good it is to be in a state S under policy pi. So to have a mathematical measure of this thing, we calculate the state value functions. Okay, and by measure we refer to the expected return. Okay, by how good I mean the expected return that I will get from a state S and following a policy pi. Or if I want to measure the how good it is to be in a state S under policy pi, then also I will measure the action value, the state value function. So state value function, value of state S in a policy pi denoted by V pi S, is expected return when an agent is in state S and follows a policy pi thereafter. So it is a measure of goodness of a policy pi being followed from a state S. So mathematically this state value function is represented in this form, that is the expected value of the return from a state S, the expected value of return from state S under the policy pi. That is, in a state S you are following a policy pi, then you want to measure the expected return that we measure by state value function, that we denote by state value function. So we can expand this return in this manner: summation of all k from 0 to infinity gamma k rt plus k plus 1 given the present state is S. This we already mentioned, this we already covered in the previous slides, that this is written in this form. So it is the expected value given that an agent follows a policy pi in a given state S at a particular instant t. So it is also known as a state value function for a policy pi. Now comes the action value function. So suppose you are in state S and you choose a particular action A, and then you make a transition to next state as t plus 1, and from this state you follow the policy pi. So how good it is to take a particular action in a present state and then make a transition to next state, and from that state to follow a policy pi. So the measure of this thing is this action value function. We denote it by action value function q pi s comma I. That is, in a given state S you take a particular action A, you make a transition to next state, and thereafter you follow the policy pi. So value of taking an action in a state S under a policy pi is the expected return when starting from S, taking the action A, and thereafter following the policy pi. So we can expand this thing. It is the expected value under a policy pi summation of all k from 0 to infinity gamma k rt plus k plus 1, provided you are in state S and you are taking action A. So this we denote by the action value function for a policy pi. So this is a mathematical derivation for the value function. So here is a mistake. This is not t plus k plus 1, this t plus k plus 1, this is t plus k plus 2. Here also please make correction, this is t plus k plus 2. Okay, I'm not going to change it in the slide. but please make sure this is not rt plus k plus 1, this is rt plus k plus 2. Okay, so please make this correction while reading the slide. This is rt plus k plus 2. Okay, so this is your value function. This is a mathematical expression for a state value function, and this is the return. We write the return in this form. So this is the expected value of the return under policy pi from state S. Okay, and now this can be expanded as rt plus 1 plus gamma times rt plus 2 plus gamma square times rt plus 3. So from this expression we are explicitly taking out this rt plus 1 term, and then again we can write it in this form. Okay, and now this is the expected value of the return in a state S. So this expression will now handle every possible state, every possible action in a given particular state, and every possible next state. So suppose you are making a transition to state, say S dash, that is your st plus 1 is S dash. So now you will select a particular action for making this transition, that is from state st, which is S. You select a particular action A and you make a transition to next state S dash, that is st plus 1 is S dash. Okay, so now I want to write this thing in this form. So let me explain you. From this state the action selected is A, the present state is S, and the next state is S dash. Okay, so that is your rt plus 1 is RASS dash. Okay, that is what is the meaning of this thing? This thing denotes that you are in state S, you are taking action A, and you are making transition to state S dash. So what is the value of the reward? So the reward is rt plus 1, and that we are denoting by RASS dash, and rest of the term is same. This term is same, and only thing that is changing is we are now explicitly mentioning that our reward, that our next state is S dash, that is st plus 1 is S dash, and we came here from this state S. Okay, this thing is incorporated in this term. So now this state S dash belong to this set. This set. So now so this S dash and small s belong to this capital S, that is set of all possible states, and this denotes the set of all possible actions. Since I am calculating the expected value of the return, so now I will have to consider each and every possible states S dash, that is S dash belonging to capital S. I have to consider each and every possible transition state, and in this state S, I will have to consider every possible action that I can take in a state S. Okay, so for mentioning these two terms, I am multiplying this expression with lambda and theta. So these are the decision parameters, and in the next slide I will show you what this means. The things I have already mentioned. Analyzing equation 1, we explicitly stated that the next state st plus 1 is S dash. We are explicitly mentioning that st plus 1 is S dash. But there could be any possible next state resulting from action AT taken in a state ST. So you were in state S, this thing is noted here, you were in state S, you took a particular action AT, you took this action AT, that is A, and you moved to the next state S dash, that is st plus 1 is S dash. There could be any possible S dash belonging to S. Okay, therefore we need to consider each possible next state S dash, which is belonging to set S, that is set of all possible states, and probability of occurrence of each state, since we are calculating the expected return. Okay, so basically this theta term will incorporate the probability of each possible next state. So your theta denotes summation of all S dash belonging to S, PASS dash. So what this expression is denoting is, you were in state S, you took a particular action A, and now you are moving to state S dash, which is coming from some distribution, say distribution D. Okay, so now